Hello AS Math, it is Mr. Knight yet again, and we are switching gears from coordinate geometry, and we are going to look at arithmetic progressions. Here's our skills today, our vocab. Really what I want to do, because it's a completely new topic, so I just want to do some kind of warm-up question. And I really want to look at our book for this. So in our book, hello book, we are going to look at these four sequences down here. They might be kind of hard to see. These four sequences, and we are going to match them with these four pictures, okay? We're going to try to identify which one goes with which, and then I also want us to describe the pattern and just kind of see what's going on and get a general idea. I encourage you to pause the video and give it a go. Alright, we're back. If you didn't pause the video, that was just an awkward transition. Hope you had a good time. Let's look at this first one. 5,000, 10,000, 20,000, 40,000. It is doubling, right? It is doubling, and to me, that just screams Asian savings. Am I right? Yeah, so it's doubling your money every 10 years, and our pattern's doubling, so this one matches with that one. The second one, 8, 0, 10, 10, 10, 10. It doesn't look like it has a distinct pattern. To me, this looks like fish and chips. Right, the first day they're open for 8 hours, then Monday they're closed, so they're there for 0, and then Tuesday through Friday they have 10-hour shifts. So that to me is fish and chips. This third one right here, it's positive, and then it goes negative, and then it goes back to positive. It's kind of going back and forth, oscillating. To me, that is this grandfather clock right here with its pendulum. It can go positive, back to 0, to negative, back to 0, positive. Which leaves us with this fourth one, 20, 40, 60, 80, 100. That looks to me like it is adding up the lengths of all of these steps together. And I'd actually like to take a closer look at that sequence, that fourth one right there. Thank you, book. Let's take a gander at this guy. So, if we're looking at this, the pattern we notice is that it's adding 20 every single time, right? It's pretty easy to see. So this guy right here, this describes a sequence. A sequence is a set of numbers in a given order, right? That's all this is to us, but it's also a special type of sequence, which we'll get into in a little bit. And each of these numbers is referred to as a term, which is just a number in a sequence. So we're going to be using this vocab throughout the remainder of these progressions and sequences, so it's a good idea to write them down or at least have an idea about them so we're not confused with the terminology. Well, let's move forward with this guy. So there are sequences with fixed patterns like this. If it's a sequence with a fixed pattern, we actually call that arithmetic. It looks like arithmetic, right? If you think of arithmetic, that's kind of our basic math foundation, right? That's just counting things, essentially. So it's a fixed pattern of counting. And plus 20, because we're adding 20 every single time, that is what is known as the common difference, right? The fixed amount that gives a sequence its pattern when it comes to arithmetic progressions, okay? So plus 20 will be our common difference in this sequence, right? So if we're looking at sequence 4, there's a couple ways we can actually write it. There is a mathematical notation to it, which we will go over in a little bit, but just kind of get an idea of what it is. We got this sequence. We're starting at 0. We're adding 20 every single time, and this is for k equals 1, 2, or 3. So basically, if I want like the second term in the sequence, I could say my k is equal to 2. I could plug it in, and I would get 40, which is the second number in the sequence. Likewise, I could do it this way too. I could write it this way. This way I could write, if I wanted the first term, I just put 1 in there. This whole thing goes to 0, and then I add 20. 20 is the first term in my sequence. For k equals 3, this is kind of how you would write it. So to read this off, this is kind of weird, but you would read this as use of k, okay, use of k, equals this stuff over here, right? So here's another example for k equals 3. Use of 3 equals 20 times 3 minus 1 plus 20. And then we get 60 as our third term. Okay? So let's actually get this notation figured out. If we can't do that, then we're going to be pretty lost. So let's take a look at it. This is notation that you're going to see in your book a lot. All right? The first term is mu sub 1, also known as a. They might just refer to it as a. Number of terms, that's n, like the n terms, right? And then the last term, mu sub n. So if I have like 5 terms, right? I have a number of 5 terms, then I'm going to have mu sub 5. And that'll be my 5th and last term. Similar to the first term, our last term can also be written with an L. The common difference is simply just D. And our general term, or the kth term, is mu sub k for term in that kth position. So if you want the 5th position, the 5th term, this would be mu sub 5 for the term in the 5th position. Okay? So now let's actually apply this notation. Let's see what this stuff will look like, and let's build towards something that's a little bit more concrete. Because right now we're just kind of taking shots in the dark, and you're just kind of seeing examples, right? So let's say I have this arithmetic sequence, 5, 7, 9, 11, 13, 15, 17. Well, I know what my first term is. It's mu sub 1, it equals a, and it equals 5. But I can continue this on. I know mu sub 2 is going to be 7. But we could write it like this, right? Now I'm adding on my common difference of 2 to my first term, and 5 plus 2 will give me 7. I continue further, the third term. Well, now, to get to my third term, I'm starting with my first term, 5, and now I'm doing the common difference twice. So I have to multiply my common difference by 2. I got to add it to my first term. I get 9. And you can start to see a pattern develop, right? And actually, if I were to continue this pattern forever and ever and ever and ever, this is what I would end up with, guys. I would end up with mu sub k equals a plus k minus 1 times the common difference. And that'll give me any term in an arithmetic progression. If you want the 512th term, you can use that to get that. Likewise, if you want the last term, this is L equals the first term plus n minus 1d. It looks exactly like the one above, with the only difference being this n, which is obviously your number of terms, which we talked about up here. So again, if I have 80 terms and I want the last term, I want the 80th term. I want however many terms there are to get my last term. Saying term quite a lot, so it's going to get weird in a second, just like saying terms so much. This isn't too bad. Let's move forward, and let's actually look at an example. Okay, so this is our first example. This is skill 1. This is finding the kth term, right? Finding the kth term. If we want to find the 17th term in an arithmetic progression, well, I have 12, 9, and 6 right here. I know my first term is 12. And I know my common difference is negative 3. It's going down. And so I'm going to use that general formula to kind of help me figure this out. Well, I want the 17th term. So I'm going to write this as mu sub 17 equals 12 plus, well, k has to be 17. I wanted 17 terms, minus 1 times negative 3. And so if I work this out, I do 12 plus 16 times negative 3. Make it easier on yourselves, ladies and gentlemen. I end up getting negative 36 as my 17th term. And that does make sense. As I move forward with my terms, I'm getting smaller and smaller and smaller. All right? Well, now, what if I wanted to know how many terms I have, right? Not just the kth term or the 17th term, What if I want to know how many terms I have just in total? So what if I gave you something like this? With skill 2, right? Finding how many terms. How many terms are in the sequence 11, 15, 19, 643? Wow, that jumped really quick. Okay? There's probably a lot, but let's find out exactly how much a lot is. Well, I know my last term is 643. I know my first term is 11, and my common difference appears to be 4. And so if I use that other equation that I wrote down earlier below my general form, right, my last term equation, I could use this and solve for it. So now I'm going to substitute in 643 equals a is 11 plus n minus 1 times 4. And if you look, I'm really solving for n, which makes sense. I'm looking for how many terms, right? That's what we said in our notation, that's the number of terms. So let's go ahead. I'm going to subtract the 11 over. I'm going to get 632 equals 4 times n minus 1. Divide both sides by 4. Probably going to need a calculator for that. I end up getting 158, which equals n minus 1, and then I have to add 1 over, so n equals 159 terms, which is quite a lot. Good thing we have math. Good thing we're not just doing this over and over and over again. That would be insanity. Okay? So now let's look at this guy right here. If I actually want to find the number of terms in an arithmetic progression, here is an alternative way to write it. So you don't have to just use this equation. This is a quick little way of going about it. And in fact, it really just comes from this guy right here. It's just another way of writing it. But use it and write it down because it might make your life just a little bit easier. And that's nice. So now, what if I wanted to take all these terms and add them together? Okay. For the interest of time, I'm going to go ahead and I'm pretty much just going to give you the formula, which I don't like doing that, but I really just want you to be able to use the formula, not necessarily to see how it's derived. Okay. So skill 3 is finding the sum of a sequence, which brings us to summing sequences, which is called series. So if I took the series of something, that is just the sum of the terms in a sequence. Okay? So let's see what that would look like. And we have 2 different equations to help us out. Okay? They look crazy. They're really not that bad. So this is the sum, or the series, of n equals 1/2 n, and then times 2a plus n minus 1d. So it still has all those components and that notation that we did earlier. Now it just looks different, right? So let's actually use it. Let's see what it's going to look like in practice. Let's find the sum of the first 100 terms of this progression right here. Well, let's think about it. I know what my a is. My a is 1. And I know what my d is. My common difference is going to be 1/4. And I know that there's 100 terms in there. So that guy's got to be my n. That's my number of terms. So if I write all those down, well, I have a, d, and n. And if I look at my formula, a, d, and n. That's all I need to be successful here, right? So now, if I use this guy, let's actually see what's going to happen. What's going to be the sum of this? So I'm going to do 1/2 times n, which was 100, times 2 times, well, we had 1. Well, that's good. Plus 100 minus 1 times a common difference of 1/4. Wow, that is a lot. So when you're putting this in your calculator, try to avoid putting it all in at once because you're probably going to make a mistake if you do that. Break it down into parts. So I'm going to clean this up a bit. I know 1/2 of 100 is 50. I know this is 2, obviously, and this is plus 99 divided by 4. Okay. From here, this is where we definitely want to use a calculator. Let's just add this inside, then multiply by 50. Now that we have something easier to work with, I'm going to do 99 divided by 4. I'm going to add my 2, and then finally I'm going to multiply it by 50, and I get, whoa, I get 1,337.5. And that does make sense. I'm getting progressively bigger, although it is a small progression. I'm getting a little bit bigger every time, and if I take 100 of those, I add them all up, I can expect to get quite a large number out of this. Good luck on your homework. Use these skills to help you out, and I'll be walking around helping you in class.